Okay, you got to get to it, you got to get to it, you got to get to it. You've got to get to quantum and atomic and nuclear physics. If you taught physics B like I did once upon a time, a lot of teachers didn't get to quantum and atomic and nuclear physics. They would run out of time before that. You've got to get to quantum and atomic and nuclear physics. And if you get to quantum and atomic and nuclear physics, but you haven't done thermo or fluids yet, I would encourage you to get to thermo and fluids too. There's no reason not to see every single topic this year. Hi, welcome. It's AP Physics 2 Training, National Math and Science Initiative. We're going to do an overview of quantum and nuclear and atomic physics. My name is John Frensley. I teach at Prosper High School in Prosper, Texas. I'm going to let you see my advertisement about my Facebook page in case you haven't liked it yet. Remember, you're encouraged to refer your students there. Questions every day, sample questions, solutions on Saturday. Okay, what's the focus of quantum, atomic, and nuclear physics? Small scale systems. Your focus, teach that light is a wave, and that light can also be a particle called a photon. Discuss the photoelectric effect, where we first found out the particle properties of light. Energy levels of atoms, how atomic spectra are made, emission spectra, absorption spectra. Back to treating light and energy as discrete, coming in little packets. That's what discrete means. Wave-particle duality, especially for electrons, protons, and neutrons. This is new. How do you read a quantum wave function? Well, we'll find that out. Nuclear forces and binding energy. What does it mean to have binding energy? What are the nuclear forces? How do those protons stay in the nucleus if they're all positive and repelling the heck out of each other? Well, you got to discuss that. Nuclear reactions and decays, alpha, beta, gamma. How to read a decay equation. How to discuss the probability of a single decay, or how to interpret half-life for radioactive decays. Make sure you're discussing all those things. It's 10%. I don't think it's a bad 10%. I think it's a very worthy of your time 10%. It's about 3 weeks. I'd say 3 weeks on atomic physics, maybe, one of the 3 weeks is on atomic physics. One of the 3 weeks is on quantum, that's like wave-particle duality, wave functions and that kind of thing. Electron diffraction. You remember I made a big deal out of diffraction in Module 5, Part A? That would be part of my quantum week, and then a week on nuclear reactions. All right. Give a decent amount of time to these topics, and if you get to quantum and atomic and you still have thermo and fluids to do, man, make sure you're doing thermo and fluids, okay? All interactions on the atomic level are governed by probability. That's big idea number 7. Don't forget that there are now 7 big ideas in physics 2. Same 6 as in physics 1, and number 7. In certain situations, probability and statistics are all we can talk about. So, this is a sentence I say a lot to my students. We do quantum and atomic and nuclear physics. I cannot tell you for certain what will happen. The best I could do is tell you the probability of each possibility. What do you mean by that? Well, I want you to imagine like you have 3 energy levels. Here's the ground state. I know you can't see it in the camera, but you can imagine it's here. And then you have your 2 excited states. I have an electron right here where my nose is. What could the electron do? It could jump down, and then it could jump down to the ground state, or it could jump down 2 levels, skipping one to the ground state. It's possible to jump, or to make a big jump. Well, which one's going to happen, Mr. Frensley? I can't tell you. I can only tell you the probability of each possibility. A single jump or 2 jumps. How long does the electron wait before jumping down? I cannot tell you how long it takes for the electron to decide to jump down. I can only tell you the probability of 1 second, 1 microsecond, 1 nanosecond for the electron to decide to jump down. I can't tell you what's going to happen. I can only tell you the probability of each possibility. Light and matter are both waves and particles. You got to make sure they understand that. It's very strange. A wave can interfere, diffract, and form standing waves. That's what a wave does. A wave can only allow certain vibrational modes, harmonics. Both light and matter have been observed to do this. Matter, like electrons, have certain harmonics in the atom. That's where you get your 1s, your 2s, your 2p, and your 3d, and all that stuff from. waves can interfere. Well, the probability waves of electrons interfere. There are some interferences that result in zero probability. There's zero probability that an electron can be found outside of 1s, 2s, 2p, and those kind of places. Okay. Particle has momentum. A particle can collide with things, and in its collisions, the particle can impart momentum to other objects. Both light and matter have been observed to do this. You want to see matter collide? Go to a pool hall. But when light collides with things, that's like the Compton effect, where a little photon can hit an electron, give the electron some of its momentum. I would make sure you have a little discussion about that. There are certain interactions that only make sense if light is a particle. Photoelectric effect, we have to treat light as photons for the photoelectric effect. Atomic emission spectra, absorption of photons, only makes sense if light is a discrete packet, a particle. The thing called Compton scattering is worth discussing. Look it up if you're not familiar with it. Certain interactions only make sense if matter is a wave. For example, the orbital structure of the electrons in the atom. Why do the electrons orbit in certain frequencies, in certain orbits? Because those orbits are like the certain standing wave modes of the electron. The fact that electrons can diffract, and so can protons and neutrons, only if matter treats as a wave. And all of quantum mechanics relies on probability. The probability of finding an electron at a certain location is dictated by a wave function. Make sure you teach your students what a wave function is. When an electron jumps down energy levels, you heard me talk about this, we don't know when or using what sequence of transitions the electron will jump down. I can only tell you the probability of each possibility. When an atomic nucleus is unstable, the atomic nucleus is going to decay, alpha, beta, gamma. When is it going to decay? I don't know, probability, possibility. It gets to that point where I just say those two words and the students know what the sentence is. We only know the probability of the decay in 1 second, happening in 1 second, happening between 1 and 2 seconds, happening between 1 or 2 years from now, happening in the next nanosecond. I can only tell you the probability of each possibility. And of course, the behavior of atoms and nuclei depend on their structure. The electrons around the nucleus determines how the electrons interact with photons. The structure of the electrons, the orbitals, determine how the photons, whether they'll be absorbed or emitted, or if they'll just pass through. The electrons are structured differently in isolated atoms than in atoms in a bulk material. The electrons in a chunk of metal behave and are structured differently than the electrons in isolated metal atoms, like a gas of iron. If the iron was a gas, then the electrons are structured such that they can give us atomic spectra. But in a slab of iron, they can undergo a photoelectric effect. So electrons versus free electrons that aren't even bound to any atoms, which can give us Compton scattering. The energy released by a nuclear reaction depends on how the nucleus is structured, okay? And I'm not just talking about protons and neutrons in the nucleus, but how many are there? Are there too many protons, too many neutrons? Is the nucleus too big for its britches? Or is the nucleus too small? Is it like hydrogen and helium? They want to get together and make bigger nuclei. All nuclear forces require, what do you want to call it, the sacrifice of some mass in order to bind the nucleus together and oppose the repulsion of the electrostatic force. How much mass turns into energy? That's Einstein's E equals mc squared. Make sure you teach it and do some practice with it. Okay, if you're just now coming in, go back to 4A, Module 4, Part A. I'll explain the serial numbers and how you can use the serial numbers to find the source of the exam question. Haven't seen a lot of photoelectric effect yet, but it might come. I don't know. Just one example on the prototype practice exam that was never used as a real exam. Other than that, I'd be happy for you to look at some of these multiple choices from old B exams and these free response from old B exams. Use them with your kids. I feel like your students need to be able to plot a kinetic energy versus frequency of light graph, come up with Planck's constant for that, and be able to talk about how the graph will change for different work functions. I think they need to do that. Atomic spectra energy levels. And a lot of those. There's a lot about energy levels. Make sure you talk about it. And if you want to give your kids some extra practice, here's some really good free responses from old AP Physics B. There's one on the 2011 exam. It's still online. You can find it. That's one that I highly recommend. These are some good multiple choices too. Dealing with absorbing and emitting photons from energy levels. Treating electrons as waves, which I call wave-particle duality. It has shown up a bit on P2. Here's some good free responses from Physics B that I feel like could be used in Physics 2. So go see them, read them, and you'll know how they are asked on the AP Physics 2 exam so far. Quantum wave functions. You won't see any quantum wave functions on Physics B. They didn't have them. However, we've seen enough of them in Physics 2. Actually, one on every single released exam. There's released AP course description, practice exam that was never used as a real AP exam behind the audit wall, and one for each year from behind the audit wall. Go see them, see how they're going to be asked. Nuclear reactions. Why is there so much P2 here? Because nuclear reactions is a pretty broad brush. Talk about alpha, beta, gamma decay. We're talking about mass converting to energy, energy converting to mass using E equals mc squared. Dealing with half-lives and decay charts, things like that. There's a lot of that. Make sure you cover it. See how it's asked on the AP exam. In part C of this module, I'm going to show you some ways that you can use certain devices in your class to simulate random processes. If you want to get actual nuclear material, I guess you can. When I was in high school, my high school teacher brought out a little disc of some kind of uranium or whatever, and we counted its decay, and we were able to come up with with an exponential decay chart. But I feel like in this day and age, I don't know a lot of teachers who still do that. I know that that teacher has not done it for almost 20 years. And yeah, that's how long I've been outside of high school. Okay, I look younger, right? Emission spectra. Your chemistry people will hook you up with a gas discharge tube, I hope. I'm going to show you that in Module B. Gosh, do you have the expensive photoelectric effect lab set up? I don't. Like $400. So if you got one, do it as a whole class lab. However, if you're cheap, like me, I have an alternative. It's called the Photon Energy Lab. It's cheap. Half-life lab if you have the stuff for it, or a simulated half-life, maybe using PhET or something like that. On paper, just doing the calculations, calculating energy, mass defect energy, drawing representations like kinetic energy versus frequency graphs for photoelectric effect, drawing energy level diagrams, doing calculations, what frequency photon will excite this atom or whatever, half-life and decay curves. I don't think there's going to be a lot of dealing with half-life for like weird amounts. So in other words, if you have an object whose half-life is 4 days, they're not going to ask about what happens after 3 days. They're only going to ask about what happens after 4, 8, 12, 16, 20, and days like that. So no weird exponents or logarithms or anything like that there. Okay, so very worth doing. If your kids are taking Physics 2, they probably want to learn this stuff. So if for no other reason, let that motivate you. Try the best you can during these three weeks of atomic and nuclear and quantum physics. I'm going to show you some things that I do hands-on in lab in the next 2 modules. Maybe there's something you can do. I'll see you there.